Thank you for the introduction, Robert. Good morning, everyone. I'm Yingpang Frederick from DRR. So now I just start to present our work, the work from Michael and me. So through the introduction, as actually you all know, the application of real-time traffic platform to monitor and control traffic state has become actually a standard part of traffic management for big cities. And more real-time data from different sources becomes available, and it is also one of the essential components in the real-time traffic platform. But actually, they are still point-wise and point-wise measurements. So therefore, simulation is still an adequate support tool to provide area-wide traffic state. But however, as all you know, it requires quite detailed actual data and has difficulty to get a varied daily traffic demand and to consider unexpected events. So online calibration with sensor data is a way to reflect traffic state in simulation. So actually there are already several online calibration tools in practice in our past fundamental project, Verbena and Verbena++. Such an open and online calibration process was also established mainly by Michael. So that we would like to use this tool, of course, for other projects. And just like many other Chinese cities, City Huainan is also in a very prosperous development phase. So this city is currently building its ITS system with real-time traffic and emission platform. So where DRR's KeepMoving portal and the online calibration process with SUMO are adapted. And then the later one is further enhanced and extended according to the project scope. So to the basic concept of the online calibration with SUMO, this process consists of two parts. The first one is data processing, and the other one is simulation, calibration, and prediction. So they are actually two independent parts and executed separately, but with the same script. So in the data processing, it includes data correction, gate filling, data aggregation, fusion, and prediction. And all results are sent to and stored in a given database, such as Postgres or Oracle. And during the simulation, the respective data from the given database will be retrieved for calibration and prediction again. And the simulation outputs will then be sent back to the same database. And all this output data can be visualized, for example, in the KeepMoving portal. So, and by the way, all the table variable definitions, customized functions, and the settings for data processing, simulation, and database connection are defined in one executable script and also in a separate file, configuration file. Yes. So let's get a closer look at the online data processing part. Here you can see the processing diagram on the right-hand side. After starting and reading the settings, the online data will be processed according to data type. So one is FCD, where only speeds are available. And the other one is stationary sensor data with speeds and floats. So they will be processed separately. And regarding the data aggregation, data is processed at age and the interval level. So data quality value will be also calculated as well, according to, for example, the raw data's existence. And moreover, two vehicle types, passenger car and trucks, can be considered here. And the data fusion and the data extrapolation are actually optional, and it can be activated by adapting the settings in the configuration file. So all processed data outputs are stored again in the respective database, and actually in the database table as shown here as an example. So to the online calibration part with SUMO, the processing diagram again is indicated on the right side. before starting it, actually the network and the traffic demand preparation works need to be done. And accordingly, routes per interval and the routes set for calibration need to be prepared as well. And then we can start this process. After starting and reading the settings, simulation will run with firstly static data, that is demand and network. And then in each interval, measurements which fulfill the predefined quality threshold are retrieved. When the data is available, the respective stage speeds will be adjusted. And if there are two less vehicles, vehicle with routes sampled from the calibration route sets will be inserted on the respective ages. And if there are too many vehicles, the sampled vehicles will be just removed from the simulation. So both adjustments are executed actually in a defensive manner. That means the simulation will try to remain unaffected until the end of the interval. So after that, the resultant age-based speeds, flows, and emissions will be sent back and stored in the database. And actually, when the whole process will continue to run until the predefined time period is reached. So in practice, this process continues running for each day. It is same like what we did for the data processing. So just as I mentioned before, we use this online calibration process in the project ITS Huainan. So I just want to give you a very, very short overview about this city. City Huainan is here you can see as marked in red on the Google Maps. It is a mid-sized city in China, and it is around 500 kilometers away from Shanghai. I hope you have the idea where the city is. And now this city has like 3.4 million residents. So actually that is 46% more than the number of residents in 2010. So you can imagine actually the city is growing very fast. And there are many different land use developments and redevelopments. And also the city is also extending its transportation system and network. So as shown in the bottom left picture, the real-time traffic monitoring platform actually consists of cameras. Here you can see, and then the KeepMoving portal, where the police can see traffic state and prediction, and the respective emission amounts, accessibility map, and the live streams at selected intersections and the road segments. So the available online data include actually FCD from Texas and the project partner, as well as data from sensors. So they will be used for calibration. Here you can see the overview of the data distribution in the bottom of left figure. Actually, we have three different kinds of data sources. And the bottom right figure, you can see the sensor group locations. Most of the detected groups are actually in the Old Town area. So it also implies that the simulation and the calibration performance will be severely limited outside the Old Town area. And to the simulation network, the OpenStreetMap in 2019 was used as simulation network base. Unfortunately, the network quality was not smooth. So it is further manually adjusted according to the detailed road geometries in the Old Town and the New Center area. They are marked in blue in the right-hand side network. Here on the left-hand side, you can see an example how detailed the road geometries are. And we also use traffic light information from the project partner and the satellite pictures from Google Maps and the images from Baidu Maps. So totally, there are around 10,000 edges and 5,000 nodes with a total length of about 2,600 kilometers. Regarding traffic demand, the use traffic demand is based on the transportation planning work done in 2009 in China. And there are 81 traffic analysis zones, TATs, were defined. and are indicated in the right figure. However, only a peak hour PCE matrix is available, and this matrix was estimated for 26 aggregated zones for 2020. So therefore, this matrix was further disaggregated for 81 TUTs according to the respective TUTs populations. And we also used the detected 5-minute flow distributions both weekdays and weekends to derive time series flow patterns and use them to generate daily vehicle trips. So the total number of trips is around 1.34 million. To simulation, calibration, and prediction, the interval for simulation and calibration was set to 5 minutes, and the interval for prediction was then set to 30 minutes. And here we use the mesoscopic SUMO for application, and moreover, data processing for taxi FCD and the stationary sensor data is also in operation here, and the fused data is used for calibration. So up to now, the simulation duration for each 5 minutes interval is usually between 70 and 90 seconds, and the maximum duration is around 130 seconds. And the total required time for data processing, simulation, calibration, prediction, and output writing to the database is less than 5 minutes, and it corresponds to the expected performance. So currently, the whole platform is under the testing and maintenance phase. So we took 2 weeks data in the beginning of this year to examine the calibration performance. So when looking at the data at 5-minute interval, we used absolute relative error for evaluation. Around 80% of the calibrated flows and 95% of the calibrated speeds have an absolute relative error less than 15%. And we also evaluated the flow data at hourly level with empirical GH statistic. And the result shows that around 92% of the calibrated flows have a GH value less than or equal to 5. So it indicates a good fit here. And on the right-hand side, we would like to show some comparison examples. The blue color indicates measured flows. The red color means simulated flows. And the fused speeds are indicated in green, and the simulated speeds are shown in yellow. So figure A and B show actually the quite promising calibration results for both flows and speeds when the data is available, of course. And figure C shows a situation with flow underestimation from the simulation. Actually, it may be due to that congestion raises in the simulation, and the calibrator cannot insert more vehicles into the network. But sometimes we also notice that it may occur due to other reasons, such as speeds are set too low due to the lower accuracy of detected speeds or the lower quality thresholds. And in figure D, only partial flows were calibrated due to the absent measurements in the afternoon and in the night. So with the FCD supplement, the speeds in the afternoon and in the night can still be properly calibrated. So to my last slide, to summary and remarks, according to the project scope, actually we have extended and enhanced the whole online calibration process, especially in the emission part and also in the part to read aggregation output for a second network for the Chinese partner, and also the extension to use Oracle database. And sometimes vehicle insertion cannot be carried out during calibration. It is not only because of lack of space on edges, but also due to that, as I mentioned before, the simulation keeps a defensive manner not to change simulation state until the end of each interval is approached. So under this circumstance, the current analysis result indicates that the overall performance is still quite fairly good. So as mentioned before, land use and network structures are continuing changing, and more people own and use vehicles in city Huainan. So it results in changes in traffic demand and also in travelers' route sets and route choices. Therefore, the simulation network needs to be continually updated for reflecting actual traffic state. And also, it is really necessary to re-examine the task definition and update the daily traffic demand data, either with the conventional traffic demand modeling method, or perhaps with other data sources, such as wiki data, mobile phone data, social media, and so on. So afterwards, the overall online calibration prediction performance will be benefited. So that's all from my presentation. Thank you for listening, and the question and comments I will come.